In this video, I'm going to show you how to use this type of ultrasonic emitter and sensor to be able to measure distance with it. For this setup, we're going to need an HC-SR04 ultrasonic sensor, an Arduino UNO microcontroller board, 4 male jumpers, a circuit breadboard, and a laptop or desktop personal computer. Before we begin, we must familiarize ourselves with the ultrasonic sensors terminals in order to understand the function and purpose of each. First, we have the VCC, or the voltage of continuous current. This is the positive polarity power supply. Next, there's the RX trigger. This controls the activation of the ultrasonic speaker. Next, there's the TX echo. This terminal sends an electric signal when the microphone senses the ultrasound pulse sent by the speaker. And finally, there's the GND, or the ground terminal. This is the negative polarity power supply. So what exactly is meant by the words trigger and receiver? Well, as it may be imagined, of these two devices mounted on the circuit board, the one on the left is a speaker, which uses electric energy with which to generate a sound of such high frequency we cannot hear, thus the name ultrasound. While the one on the right is a microphone, which receives the ultrasound vibrations and converts them back into electric energy. Having understood that, let's move on with the connection diagram. First, let's check out the power supplies. This wiring diagram makes use of two power terminals on the Arduino circuit board, namely the 5-volt pin for a positive polarity supply and a GND pin for a negative polarity supply. Now, let's continue with the control terminals, namely the 8th and the 9th terminals of the Arduino digital pins. In this case, the 9th pin is used to send a signal towards the sensor's trigger, while the 8th terminal is used to receive the signal that will be sent by the echo terminal. So now, let's proceed with the C code to program the functioning and communication between the Arduino and the sensor. First, let's start with the declaration of variables. We have the constant byte trigger equals 9. This is going to be used to select the 9th digital terminal. Next, there's a constant byte echo 8. This is going to be used to select the 8th digital terminal. Then there's the long time. This is going to be used to store the value of the time it takes for the ultrasound to be generated by the trigger and then be sensed by the receiver. And finally, there's the long distance. This is going to be used to store the distance between the sensor and whatever surface the ultrasonic pulse bounced off of. So now, let's check out the code inside the void setup function. First, the serial communication between the Arduino and the computer is set with 9600 bauds. Next, The pin mode for the trigger, output mode, sets the ninth terminal to output a power supply. Now, the pin mode, echo, in input mode, sets the eighth terminal to listen for an incoming signal. And finally, a digital write for the trigger, low output. This sets the ninth terminal to output a negative power supply. The reason the ninth terminal is written with a low state is because, since the trigger terminal on the ultrasonic sensor, meaning this one, requires a positive polarity in order to power the ultrasonic speaker, a low state for the ninth digital terminal is equal to turning off the speaker. Let's move on with the third and final code block. But first, we must understand that the void loop function cycles back the code written within it indefinitely. Therefore, once the Arduino is finished executing the last line of code, meaning this one, it will go back to the first one and begin again. The first line writes a high state on the trigger terminal. This will, as explained before, power up the speaker. The delay microseconds 10. This line stops the Arduino from executing any further code for the defined time length. In this case, 10 microseconds. And another write upon the ninth terminal. This is again a command to output a negative polarity, powering down the speaker. So, in essence, these three lines of code will power up the speaker, wait for 10 microseconds, and then power it down, thus resulting in a 10 microsecond ultrasonic pulse. Now comes the pulse in object. This is the most important part of the code. This function constantly reads the terminal that was selected for it. In this case, the echo or the eighth digital pin, waiting for a positive or negative pulse, either set for high or low state. It then calculates the time span between the execution of the pulse in and the moment the positive or negative pulse is introduced into the selected terminal. In this case, the moment the echo terminal sends a positive pulse towards the eighth pin. And finally, the variable time is then used to store that calculated value. Now, the distance equals time over 59. This mathematical division will be explained in more depth later on in the video. These serial prints are used to relay the value of the distance variable, adding to it a centimeter unit of measurement. And finally, another delay code, this one of 100 milliseconds. The purpose of this delay is to stop the re-execution of the void loop programming, so as to avoid activating the speaker far too many times within a very short time span, flooding the air with too many ultrasonic pulses. So, with the theory out of the way, let's proceed with the assembly of the circuit. First, I began by putting the ultrasonic sensor on the connection breadboard and placed all the four jumpers with their respective terminals, the VCC, the trigger, the echo, and the ground, red, orange, blue, and black. And then just connected the jumpers with their respective terminals on the Arduino board. And now, let's upload the drafted code using Arduino IDE. So finally, here's the circuit in action. The code is uploaded. I have my sensor over here, and I'm gonna use a ruler and this card to be able to measure the distance and see what measurement the program throws. So those are 20 centimeters. 19, 18, 17, 16, 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, and 1. So, there we have it. The system might need a few tweakings so as to obtain wholly accurate readings all the time, but the principles have been shown to work. Right. Before we end this video, it will be useful to discuss some of the basic physical principles involved that enable this circuit to measure distance, so as to further our understanding of the phenomena at work and help us improve upon this system. First, let's see the basic principle of acoustics, which is nothing more than the phenomenon of waves propagating on matter, in this case, air. Depending on the amount of waves, and thus the frequency, we classified sound as infrasound, or sound of such low frequency we cannot hear. Sound is the frequency inside the range we can hear. Ultrasound, and as mentioned before, it is sound of such high frequency we cannot also hear. So, the ultrasonic speaker, or just about any speaker, is in essence a generator of acoustic waves. In this case, the speaker's housing acts as a barrier against the propagation of generated waves and causing them to be redirected on a linear trajectory. This effect is known as diffraction, or the propagation of waves through obstacles. And once the waves encounter a solid body, the body absorbs some of the kinetic energy of the colliding sound waves and then releases it back into the air medium. The elasticity or lack thereof of the body plays a role on how much acoustic energy it can absorb and or reflect. Finally, the kinetic energy of the newly generated waves then travels in the opposite direction to that of the control speaker and into the microphone, whereupon it absorbs some of that kinetic energy to release an electric pulse. So, those are the basic principles at work. However, one final question remains. How do we calculate how much distance did a pulse travel? In order to answer that question, we must understand the speed of sound in an air medium. And at about 20 degrees centigrade, this speed stands at around 344 meters per second. If we multiply that number times 100, we'll get that the speed of sound stands at around 34,400 centimeters per second. Now, in order to calculate how much time it will take sound to travel 1 centimeter of length, we just need to divide 1 over 34,400. Such division will yield the value of 29.06 microseconds. That's how much time it will take sound to travel 1 centimeter. If we consider that the ultrasonic pulse has to travel towards a given body, then return, therefore, the pulse will have to travel twice the distance. Thus, we just have to multiply the original time value of 29.06 by 2, and we'll know how much time it will take the pulse to travel from the trigger to the receiver, if the body that the ultrasonic pulse bounced off of was 1 centimeter away. And, as we can see, here, 58.12, this is the value from which the mathematical formula discussed back when the third code block was analyzed was derived from. Since the pulse-in function counts time in microseconds, we only need to divide the amount of time it took the pulse to be emitted and then detected by 58.12, or just simplified into a rounded number. And thus, the distance between the sensor and the surface the pulse bounced off of can be calculated. So that's it. Hopefully, with all this information, you'll be able to more wholly understand how ultrasonic sensors work and how to program one yourself.